Hi, this is K. Lois from IDA. Today my topic is Kirchhoff circuit law. Kirchhoff circuit laws. Kirchhoff circuit law are two equations that deal with current and potential difference, also commonly known as voltage. In the 10 elements mode of electric circuit, they were discovered or described in the year 1845 by German scientist Wilhelm Kirchhoff. This generalized the work of Georg Holmes and predict the work of James Clerk Maxwell. Widely, widely used in electric engineer, they are also called Kirchhoff rules or simply Kirchhoff's law. Their laws can be applied in the time and frequency domains and the form of basic of network analysis. Kirchhoff current law, also known as KCL. This law, also called Kirchhoff first law, Kirchhoff point rule, or Kirchhoff junction rule or node rule, states that for any node in a electrical circuit, the sum of currents flowing into the node is equal to the sum of current flowing out of the node or equivalent. The algebraical sum of currents in a network of a conductors meet at the point is zero. The current entry on any junction is equal to the current leaving at the junction. Let us consider I1, I2, I3, I4. I2, I3 are coming to the junction and I1, I4 are leaving to the junction where I1 plus I4 is equals to I2 plus I3. That's we calling that current is a signed positive or negative quantity reflects direct towards or away from a node. This principle can be successfully stated as Kn is equals to 0 where k is equals to 1 where the where n is total number of branches which current flows towards or away from the node. This law is based on the convention of charge, where the charge measured in the lumps is the product of current in amps and the time in seconds. If the net charge in a region is constant, the current law will be hold the boundaries of the region. This means that the current law ripples on the fact that the net charge in a wire and compounds is constant. Uses a matrix version of Kirchhoff current law is the basic of most circuit similarity software such as Spice. The current law is used with Ohm's law to perform node analysis. The current law is applicable to internet networks irrespective of nature of network, whether unilateral or bilateral, active or passive, linear or non-linear. Let us consider Kirchhoff voltage law, also known as KVL. This law, also called Kirchhoff's second law, Kirchhoff or mesh rule, or Kirchhoff's second rules, state the following: the direct sum of potential difference voltages around any closed loop is zero. The sum of all the voltages around a loop is equal to zero. Let us consider V1, V2, V3, V4, and V5, where a V1, V2, V3, V4 is on circuit and V5 is out of the circuit, where that V1 plus V2 plus V3 plus V4 must be zero. Similar to the Kirchhoff current law, the voltage law can be started as Vk is equals to 0 where k is equals to 1. Here n is total number of voltages measured. Derivation of Kirchhoff voltage law. A similar derivation can be found in the lecture on physics, volume 2, the AC current. Consider some circuits approximate the circuits with some elements so that time variations. Magnetic fields are connected to each other compounds and the fields in the region extract to is intangible. Based on this aspect, the Max Faraday's equation reveals that. Let us consider a circuit which is under the contain of magnetic field which wants to satisfy Maxwell Faraday's equation where delta into E is equals to B by T is equals to 0. In the internal region, if each of the compounds have infinity volume, then the internal region is similarly connected. Hence, this electric field is converted into the region. Therefore, for any loop in the circuit, we find that Vi is equals to minus E into Di is equals to E into Di is equals to 0, where it is from 0 to P1, where Pi are the path around the internal of each of the compounds from one terminal to another terminal, which passes one terminal to another terminal at one end to another end. Note that the derivation using the following definition of the voltage rises from A to B, where V is equals to A raised to B is equals to minus P A to B, A tends to B, E into Di. However, the electric potential and hose voltage can be defined in another ways, such as via the Helmholtz decomposition. decomposition. Generalization. In the low frequency limit, the voltage drop around any loop is zero. There must be zero. This including imagined loop arranged in a array space not limited to the loops delineated by the circuit elements and conductors. In the low frequency limits, these are collaborative Faraday's law of induction, which is one of Maxwell equation. This has pattern application in situation involves static current, electricity. Limitation of Kirchhoff law, and the Kirchhoff law have some limitation which are results to them are the result of the dumb element mode and both depends on the model being applicant to the circuit in the question. When the model is not applicable, the law does not apply. The current law is depends on the aspects that the net charge is anywhere, junction or loop compound is constant. Wherever the electrical field between part of the current is not eligible, such as we have two wires are capacitable coupled, this may be not be the case. This occurs in high frequency IC conductors, alternating current conduct circuits, where the dumb elements modes is no longer applicable. For example, in a transmission line, the charge density in the conductor will be constant by oscillation. Let us consider. On other hand, the voltage drop ripples on the fact that the action of time variant magnetic field are conformed to individual compounds such as inductors. In reality, the inductor electric field produced by inductor is not confined, but the leaked files are not intelligence of the inductive. Modeling real circuit with drum elements. Drum element approximately of a circuit is accuracy at the low frequency. and the high frequency liquid flux and variant charges distance in the conductor because significance to an extent. It is possible to still model such circuits using parasitic compounds. If frequency are too high, it may be more approximately to simulate the field directly using infinite element model or another techniques. It must be in the frequency high. To model circuits so that both laws can still be used, it is important to understand the distance between physical circuit elements and the ideal dumb elements. For example, a wire is not an ideal conductor. Let us consider a wire which is not an ideal conductor. Unlikely an ideal conductor, wires can be considered and capacity couples to each other and to themselves, have infinite propagation delay. Real conductors can be modified in the terms of dumb elements by consider parasitic disturbance between the conductor to model capacitive couplings or mutual indistortions to model inductivity coupling. Wires also have some self-destruction which reasons to decompose a capacitor as necessary. Where wire must be an is not an ideal conductor. Let us consider a wire which was the wire is must be capacitor dual each other. It's infinity to delay. Real conductor can be modified in the terms. For example, the transmission line, the net charge is different part of conductor charge with time. In the indirect physical sense, this avoid KCL, Kirchhoff circuit law. Let us see this image. They're damaging that the net charge is different parts of the conductor changes within time. If the ones see that picture where we seen that the flow will changes at the each part and in variant intervals. This may be avoids Kirchhoff current circuit law. For an example, we analyze that assume a current network consisting of 2 volt sources and 3 resistors. Let us consider a circuit which have considered 2 voltage source and 3 resistors. The resistors are R1, R2, R3 and the 2 voltages are let us in this from the figure we observe that they have 2 node junctions. According to the first law, Kirchhoff KCL, according to the first law, I1 minus I2 minus I3 is equals to 0. Applying the second law, Kirchhoff voltage law, to the closed circuit S1. Let us consider okay, let the circuit divides into two parts. First one is S1, second one is S2. I am assume that S1 and S2 are in clockwise direction where I is equals to positive sign and at the point one node one the current flow direction is low. The current is enter into the first I1 current enter into the node and I3 I2 leaving at node 2. Apply second law to close a circuit S1 and submitting of voltage using Ohm's law given. After applying second law, R2 I2 plus sigma minus R1 I1 is equals to 0. The second law again combined with the Ohm's law applied to the closed circuit S2 given. Minus R3 I3 minus E2 minus E1 plus I2 I3 is equal to 0. This fields a system of linear equation in I1, I2, I3. This fields are systemic of linear equation I1, I2, I3. I1 minus I2 minus I3 is equals to 0 and minus R2, I2 plus E1 minus R1, I2. I1 is equal to 0. Let us consider the third equation minus R3, I3 minus E minus 2 minus E1 plus R2, I2 is equal to 0, which is equivalent to the I1 plus minus I2 plus minus I3 is equals to 0. R1, I1 plus I2, R2 plus 0, I3 is equals to E1. 0 I1 plus R2 I2 minus R3 I3 is equals to E1 plus E2. Assume that R1 is equals to 100 ohms, R2 is equals to 200 ohms, R3 is equals to 300 ohms. E1 is equals to 3 V, E2 is equals to 4 volt. The sum is I1 is equals to 1 by 1100, 4 I2 is equals to 1 by 255 amperes, I3 is equals to minus 3 by 220 amperes. The current I3 has negative sign, which means the assumed direction of I3 was incorrect and I3 is actually flowing in the direction opposite to the red arrow. Label 3. This current is R3 flowing left to right. After analyzing this sum and the diagram of applying KCL and KVL to the problem, we are solved as the solution. We rectify the I1, I2, and I3. We find the values. If it is in clockwise, we assume direction is clockwise. That's why we taken place. But I3 is opposite to our assumption. That's why it's negative sign. And thank you, sir. It's my tech talk presentation to BW about Kirchhoff circuit laws. Thanks. Thanks all.